Populations or two treatments is one of the most common situations encountered in statistical practice. We call such situations two-sample problems. So, for example, does drug A work better than drug B? Is a new teaching method more effective than the old teaching method? We know that on average men are taller than women, but how much taller? In this chapter we'll talk about two-sample problems, comparing two population means, two-sample t procedures. We'll talk about robustness of these procedures again, and some details of the t approximation. In a matched pairs design, subjects are matched and then the difference is tested. So in the case of, suppose we want to compare drug A to drug B and see if drug A works better than drug B. In a matched pairs design, there would be a sample of people, say 25. Each person would be given one drug, then reaction would be measured. Then people are given the second drug, again the reaction is measured. And we compare the difference between people's reactions. In this case, the same people essentially are in the two samples. In an independent samples design, we might say take 50 subjects, and then we randomly assign them to two different groups. One group receives drug A, the other group receives drug B. Then the two samples are compared. There's no overlap. So what if we want to compare whether test averages of morning classes are different from test averages of afternoon classes? In this case, there are two populations we need to consider: the morning class and the afternoon class. Our parameters of interest are the population means, mu1 and mu2. The best approach is to take separate random samples from each population and then compare the sample means. Suppose we want to compare the average effectiveness of two teaching methods in a randomized experiment. In this case, the parameters mu1 and mu2 are the true mean responses for treatment 1 and treatment 2 respectively. And we use the mean response in the two groups to make the comparison. So here's a table that summarizes both of these situations. We have two populations or two treatments. Each population has some parameter, mu sub 1 and mu sub 2, that we don't know and we want to know. We gather information in terms of statistics on a sample. We get a sample mean from both samples, and each sample has its own sample size. The standard way to compare two population means is to estimate their difference. If the difference is close to 0, we would conclude that the population means are about equal. If the difference is large and negative, we would conclude that the first population mean is much smaller than the second. Of course, we quantify the words close and much smaller in terms of standard deviations. So, we need to talk about a little bit about the conditions for inference when we're comparing two means. So, we have two simple random samples from two distinct populations. The samples are independent. That is, one sample has no influence on the other. Matched pairs, for example, it violates independence because we have the same subjects in both cases, in both samples. And then we measure the same response variable for both samples. Another condition, both populations are normally distributed. The means and the standard deviations of the populations are unknown. In practice, it's usually enough that the distributions have similar shapes and that the data have no strong outliers. So when data come from two random samples or two groups in a randomized experiment, the statistic x bar sub 1 minus x bar sub 2 is our best guess for the value of the difference between the population means. Keep in mind that because we get different samples all the time, the statistic x bar 1 minus x bar 2 is variable. It's going to change. The value of the difference of the population means, of course, is constant. So when the independent condition is met, the standard deviation of the statistic x bar 1 minus x bar 2 is given by this formula. So we square the population standard deviations, divide by its sample size, add that to the square of the second population standard deviation divided by its sample size, and then take the square root. Since we don't know the values of the parameters sigma 1 and sigma 2, we replace them with in the standard deviation formula with the sample standard deviations. The result is called the standard error of the statistic. So here we're just replacing the sigmas in both cases with the standard deviations of the samples. If the normal condition is met, then we can standardize the observed difference to obtain a t-statistic that tells us how far the observed difference is from its mean in standard deviation units. So the t-statistic is the difference between the sample means divided by the standard error of the statistic. The two-sample t-statistic has approximately a t-distribution. And we can use technology to determine degrees of freedom, or we can use a conservative approach. And the conservative approach is to take the smaller of the two sample sizes and then subtract 1. So when the random, normal, and independent conditions are met, a sea-level confidence interval for the difference between population means is given by this formula. It's the difference of the means, of the sample means, plus and minus a margin of error. And the margin of error is the critical value for the confidence level in terms of the t-distribution with its degrees of freedom, and multiplied by the standard error. This is pretty much the same thing we've been doing all along, it's just getting a little more complicated. Okay, so here's an example. The Wade Tract Preserve in Georgia is an old-growth forest of longleaf pines that has survived in relatively undisturbed state for hundreds of years. One question of interest to foresters who study the area is, how do the sizes of longleaf pine trees in the northern and southern halves of the forest compare? To find out, researchers took random samples of 30 trees from each half and measured the diameter at breast height, dBH, in centimeters. Comparative box plots of data and summary statistics are shown below. And we need to construct and interpret a 90% confidence interval for the difference in the mean for longleaf pines in the northern and southern halves. So we have all the data here, and we have a pair of box plots. So our parameters of interest are mu1, the true mean of all trees in the southern half, and mu2, the true mean of all trees in the northern half. And we want to estimate the difference at a 90% confidence level. So we should plan to use a two-sample t-interval for the difference between the means, if the conditions are satisfied. So we're told that the data come from random samples. We're all set there. The box plots sort of indicate that the distributions may not be normal. But since both sample sizes are at least 30, we're safe using t-procedures. Since researchers took independent samples from the northern and southern halves of the forest, the independent condition is met. That is, there's no overlap. Okay, since the conditions are satisfied, we can construct a two-sample t-interval for the difference. And we'll use the conservative degrees of freedom, the smallest sample size, in this case they're both 30, and subtract 1. So degrees of freedom, 29. And here's the formula for the confidence interval. So we need to locate the row with 29 degrees of freedom and the confidence level of 90. So our critical t-value is 1.699. So we plug in the values, the two sample means, plus and minus the standard error, And in this case, we get the margin of error is 7, and the difference between the sample means is 10.83, and we get a confidence interval 3.83 to 17.83. So how do we interpret that? Well, as with all confidence intervals, we say we're 90% confident that the interval from 3.83 to 17.83 centimeters captures the difference in the actual mean diameter at breast height of the southern trees and the actual mean DBH of the northern trees. So what does this mean? Well, in this case, we have a directionality with it. This suggests that the mean diameter of the southern trees is between 3.83 and 17.83 centimeters larger than the mean diameter of the northern trees. So we do need to keep track of which sample mean came first. Make sure that we identify it. Okay, now the two-sample t-test. So suppose the random, normal, and independent conditions are met. So to test the hypothesis that the difference between the mean is the difference between the population means is some hypothesized value, we'll compute the following t-statistic. The difference in the sample means divided by the standard error. And we find the p-value by calculating the probability of getting a t-statistic this large or larger in the direction specified by the alternative hypothesis. We've done this before. And use the t-distribution with degrees of freedom approximated by technology, or the same, we use the smaller of the two sample sizes and subtract 1. So here are the alternative hypotheses. If our alternative is that the difference between mu1 and mu2 is greater than some value, or the difference between mu1 and mu2 is less than some value, or the third option, that the difference between the two means is simply not equal to some hypothesized value. Oftentimes the hypothesized value will simply be 0. So we're looking to see if the two means are different or the same. Okay, here's an example. Does increasing the amount of calcium in our diet reduce blood pressure? Examination of a large sample of people revealed a relationship between calcium intake and blood pressure. And the relationship was strongest for black men. So this was probably a regression type analysis where we were simply looking for, trying to determine whether there was a relationship between these two variables. And in this case, they found that it was the strongest for black men. So this was an observational study, so it does not establish causation. So to investigate further, researchers designed a randomized comparative experiment. So the subjects were 21 healthy black men who volunteered to take part in the experiment. They were randomly assigned to two groups. 10 of the men received a calcium supplement for 12 weeks, while the control group of 11 men received a placebo pill that looked identical. The experiment was double-blind. The response variable is the decrease in systolic blood pressure for a subject after 12 weeks in millimeters of mercury. An increase appears as a negative response. So the two groups, here are the data, the differences between the before and the after. So we want to perform a test of the following hypotheses. The null hypothesis, that the difference between the two population means, that is the calcium supplement and the placebo, is 0. So essentially we're saying that they're the same. Or that the difference between the two population means is greater than 0. Essentially we're saying that mu1, the calcium supplement group, is larger than the placebo group. So in this case, we'll use an alpha level of 0.05. So if the conditions are met, we'll carry out a two-sample t-test for the difference in population means. The 21 subjects were randomly assigned, so we have randomness. The box plots and normal probability plots for these data show the following. So in this case, there's no clear evidence of strong skewness, no outliers, and the normal probability plots are fairly linear. So the T procedure should be good. And because there was random assignment, these two groups of men can be viewed as being independent. Since the conditions are satisfied, we can perform a two-sample t-test for the difference. So the test statistic, in this case, t equals x bar 1 minus x bar 2 minus the difference in the hypothesized means over the standard error. So in this case, the difference between the sample means, 5 minus a negative 0.273, and the difference between the population means here we hypothesize to be 0. That is, there's no difference between them. They're the same. And the bottom part of the t-statistic has the sample standard deviation, 8.743 squared, divided by the sample size of 10 for the first group, and 5.901 squared, divided by the sample size 11 for the second group. We add those and then take the square root. And that all comes out to 1.604. So the p-value is the shaded region in the t-distribution with 9 degrees of freedom. So again, we're using 9 degrees of freedom here because the smallest sample size is 10, so we subtract 1 from that. So we look at the row with 9 degrees of freedom in table C. 1.604 falls between the values 1.383 and 1.833. This is a one-sided test, so we estimate the p-value is between 0.1 and 0.05. So because the p-value is greater than 0.05, we fail to reject the null hypothesis. The experiment provides some evidence that calcium reduces blood pressure, but the evidence is not convincing enough to conclude that calcium reduces blood pressure more than a placebo. And that's assuming that the null hypothesis is true. The probability of getting a difference in mean blood pressure reduction for the two groups, the calcium minus placebo, of 5.273 or greater, just by chance, is 0.0644. Still unlikely, but not at the level that we wanted. Okay, so we need to talk a little bit about robustness again. The two-sample t procedures are actually more robust than the one-sample t methods, particularly when the distributions are not symmetric. That's a good thing. So, except in the case of small samples, once again, the condition that the data are simple random samples from the populations of interest is more important than the condition that the population distributions are normal, with notable exceptions. If the sum of the sample sizes is less than 15, we want to use t procedures if the data appear very close to normal. If the data are clearly skewed, or if outliers are present, do not use the t. If the sum of the sample size is at least 15, the t procedures can be used except in the presence of outliers or really strong skewness. And for large samples, the t procedures can be used even for clearly skewed distributions when the sum of the sample sizes is large. And again, that's somewhere around 30 or 40. So, a little bit of detail about the t approximation. Keep in mind, I'm not going to ask, you won't be asked to use any of the formula that I'm about to show you, but it's good to know. So, to calculate degrees of freedom, we actually have two options. The conservative option is to choose the smaller of the sample sizes and then subtract 1. But there's also a formula, so you should be aware that if you're using software, you will probably get a different degrees of freedom reported to you than what we've been talking about so far. So with the example we just did, we found that the degrees of freedom were 9. If you performed this t-test in Excel, it would have given degrees of freedom 15. So here's the formula. It turns out that the exact distribution of a two-sample t-statistic is not really a t-distribution. So the distribution changes as the unknown population standard deviations change. But it's very close, and we can use this value below here. Using this formula, the distribution is very close to the t-distribution given by degrees of freedom with this formula. And the approximation is accurate when both sample sizes are 5 or larger. So this is what's happening behind the scenes when you use a software package of one kind or another. Okay, some cautions here. Many of the calculators or software packages have a choice of two-sample t-statistics. One is often labeled unequal variance, the other for equal variance. We only use unequal variance as the procedure for two-sample t-tests. You never use the pooled t procedures if you have software or technology that has unequal variance procedure. So this is a conservative procedure. The equal variances procedure requires that the populations have equal variance, which is not always known, so we'd have to do some other kind of a test. They tend to be more accurate, but you really need to exercise caution because it doesn't apply in all cases. So the unequal variance procedure is the one to use. It's more conservative. Talking about standard deviations, well, there is also a method for inference about the standard deviations of normal populations. For example, are the two populations equal with their standard deviations? And if so, then we could probably use the equal variances, right? Well, the problem is that the procedure for doing this uses what's called the F-test for comparing the standard deviations. And the T procedures for means are very tolerant of non-normal distributions. The F-test is extremely sensitive to non-normal distributions. So we recommend that you do not use inference about population standard deviations. Okay, so to review, we talked about the conditions necessary for inference. We checked the conditions, performed two-sample t procedures in terms of hypothesis tests and confidence intervals. We talked about the robustness of the t procedures and gave a nice little nasty formula having to do with the t approximation. Describe why we should avoid pooled two-sample procedures or the equal variances procedures, and why we should avoid inference about standard deviations.